Okay, here's your favorite AB Chem teacher again, going over a test we just did today on electrochemistry, and I'm going to podcast this to give you a little better idea how you should do these questions. So the first question is, which element is reduced in the reaction below? So I have no idea what's going on in these two molecules, but I can tell you that the hydrogen here has been reduced because it goes from a +1 there to 0 here. So clearly the answer here is hydrogen. And probably this iron has been oxidized somehow. Okay, so which element is reduced in the reaction below? Remember, reduction is when you gain electrons. So which of these has gained electrons? First of all, let's take a look at the iron here. The iron, the number has gone up. That means it lost an electron. The other candidate would be chromium here. So let's look at the oxidation number for chromium here. It's 2 minus total, so since that's minus 14, this one has got to be +6 because I've got two of them for a total of +12. So the chromium went from +6 to +3. That means it's been reduced. Which of the following reactions is a redox reaction? That means that something has changed in charge on this. Well, it turns out the reactions A and B, if you look carefully at every one of the elements, none of them have actually changed charge. But in the case of C here, they have. The copper here is carrying no charge, sulfur carrying no charge, but yet over here the copper is 2+ and the sulfur is 2-. So the only one that's redox is C. What is the coefficient of the permanganate ion when the following equation is balanced? Okay, so this is one of those long questions, and I'll just work it out with you here. Hopefully my pen will last throughout this. Let's go ahead and do the long solution, and I'm going to first of all write out the two half reactions, and I'm going to try to be careful not to make a mistake here. So this is one of the half reactions. In this half reaction, let's see, -8. Manganese has gone from a +7 here to +2, so it's been reduced. And looks like the bromine is the one being oxidized. So this half reaction is bromine 1- goes to bromine 0. Okay, now the first thing to do here is balance all the elements that are not hydrogen or oxygen. So over here we need to add 4 waters, and as a result we need to add 8 hydrogens over here. So now I've got all the elements balanced on both sides. Over here this is good. Okay, now after you've balanced the elements, next thing would be to check the charges, because we have to figure out how many electrons are moving around. So first of all, on this side we have 8+ and 1-, so that's a total of 7+. And on this side we have a total of only 2+. That means I need to add 5 electrons to this side. So I'm going to put that down here. 5 electrons are going to be added to the 8 hydrogen ions and the permanganate ion. And over here I'll just recopy what I have. Alright, that's very good. Now over here we have to check the charges. So -2 on this side, 0, means I'm going to have to add 2 electrons to this side. Now the charges are the same, 2- on both sides. Now at this point I can combine both of these together, but here's where I have to multiply them out to get the electrons the same on both sides. I have to multiply this whole side by the number 5 because of 5 electrons. I have to multiply this whole side here by 2 because of those 2 electrons. Okay, so then let's just rewrite it all out. 10 electrons plus 16 hydrogens plus 2 permanganates. And maybe I could save a step here and just multiply that out and put it down here directly. So up here I have 10 bromines. It's actually bromide ion. Okay, so that completes this side, and then now starting with this and this combined. Here I've got 2 of these manganese plus 2s. And I've got 8 waters. And over here I have to add in this side. So I've also got on this side 5 bromines and 10 electrons. Now at this point we really do have the answer to the question, what is the coefficient of the permanganate ion? We could actually stop here. The coefficient in front of the permanganate ion is going to be 2. Now we could continue to reduce this down. Maybe we should, just to show you what it would look like. So let's see, we've got on this side, do we have any waters on this side? No. Over here we have 8 waters. Actually this is the answer just as written. So I would call it 2 for the permanganate ion. So what's the coefficient of iron when the following equation is balanced? Basic solution. Alright, well I don't know how else to do this except for the long method. So bear with me here. Let's try this one. Half reaction on this side is CnO, 1 minus. And over here on this side we've got iron 3 plus becoming iron 2 plus. Alright, there we go. Now first of all let's balance both sides in terms of the atoms. I'm going to have to add 1 water to this side because I needed to get an oxygen over here, and I'm going to add 2 hydrogen ions to this side. Okay, all of the atoms are balanced on this side. Just to balance the charges, I have 1 minus on this side, and 1 minus and 2 plus makes 1 plus on this side. So I'm going to have to add, to get this down to the negative here, I need to add 2 electrons to this side. See, now I have the charge at -1 and -1 total here. Okay, over here with everything is balanced except I do need to add electrons. Plus 3 plus 2, I need to add 1 electron to this side. So we have added 2 electrons to the right, over here 1 electron to the left. Okay, fine, let's recombine this then. I've got, oh, first of all let's multiply it out. So 2 electrons on this side and 1 on this side means, before we do anything, let's make sure we multiply this by 2. Okay, so writing it out, first let's deal with all the stuff on the left. I don't have to multiply this out because this is going to be 2 on this side and 2 on that side. Alright, so, and I need to bring in this iron plus 3 here, and I have 2 of them. So this is where I'm going to make sure I don't make a mistake. Multiply that by 2. So this should be all of the stuff on the left. 1, 2, 3, and I have 2 electrons I've got to put over here too. Okay, so that's everything on the left side. Now the right side is CnO, 1 minus, plus 2 H pluses, plus 2 electron minus. Okay, so that's this part. And over here, I've got the iron. I have to multiply it by 2, 2 plus. Alright, so hopefully I didn't make any mistakes on all that. And you can certainly check your work here. 2 irons and 2 irons, 1 nitrogen, 1 carbon. Over here I've got 2 hydrogens. Over here I've got 2 hydrogens. 2 electrons on both sides, which are going to cancel. And the charge over here is plus 3 minus 1. So total charge on this side is plus 2. And the total charge on this side, I've got 2 plus. Here I have 4 plus, you see, because it's 2 times plus 2, and then 2 plus, and 1 minus. So I've got 6 plus minus 1 for a total of 5 plus on this side. So I must be missing something here. This is 6 plus, okay, yeah. So actually this is 5 plus 2, because there's 6 plus minus 1. So the charges balance. The answer, therefore, the coefficient in front of the iron 3 is 2. So that's a long problem, but you kind of have to work it through like that to be sure you're getting it right. Which transformation could take place at the anode of an electrochemical cell? Well, if you remember, the anode is where oxidation takes place of an electrochemical cell that's generating electricity. I know that because these are both vowels, A and O. So which one of these is something oxidized? Alright, well, it's going from 0 to minus 1, that's reduced. This one, the chromium over here, is actually plus 6 to plus 2, that's reduced. Here, the oxygen is going from 0 to 2 minus, that's reduced. It's got to be this one here or this one. Let's just check this. So this is plus 1. This is 4 minus because there's 2 of them. That makes this 3 plus. And of course it goes to 0, so that's actually reduced. Doesn't seem like any of these are going to work. Reduced, 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 reduced. Yeah, E. None of them work. The purpose of the salt bridge is actually to equalize the charge of ions as they migrate. So there's the key phrase right there. So it should be A. Okay, now which of the halogens is the strongest oxidizing agent? That means it's the one that is reduced. Being the one that is the agent of oxidation means that it is the thing that's reduced. And so here is a reduction potential. See, this is gaining electrons, which is very strong. So clearly the fluorine is the strongest oxidizing agent. It's the most willing to be reduced here. Which of the following reactions will occur spontaneously as written? Okay, now obviously what that means is that the E potential must be positive if it's going to occur spontaneously. So in all of this we're looking for something where the E potential is positive. Alright, well, here we go. Let's do these individually and try not to make a mistake. So this has gone from plus 4 to plus 2. That means it's reduced. Alright, so when I come up here and I find that one, I see that this one is 0.154 minus the oxidized one. So look at this. This is 3 plus, 2 plus, so this has also been reduced. Well, see, you can't have that. You can't have this one reduced and this one reduced. This is goofy. One has to be oxidized. Okay, this one goes from 0 to plus 2. That's oxidized. So from iron to iron 2 plus is this one right here. Since it's the oxidized one, it's going to be the second one I write up here. I'm going to subtract that off from the reduced one. And sure enough, that one is reduced. So chromium 3, the chromium metal, is a negative 7.4. So let's just see, is this going to be positive in the end? So if I add a positive here, nope. See, this is going to be negative, a negative number. So this one's out. Okay, here tin 4 to tin 2, that's reduced. Iron 2 to iron 0. Wait a minute, that's reduced. They're both reduced. Here we've got tin 4 to tin 2. Okay, that's reduced. So 4 to 2 is this one. I'm going to put that out here. I'm going to subtract off from the oxidized side. Let's see if this is right. So the chromium is oxidized, definitely. And so the chromium one is minus 0.74. So that's how it's written out. Alright, let's see if this is negative or positive. So when I change the signs, I've got, this is definitely a positive. So right there I've hit one that is the answer. Just for fun, let's look at this bottom one here. Let's see, I don't know how you're going to have this going both ways. That doesn't look right. Let's just assume the answer is D. Consider electrochemical cell based on the reaction here. Okay, that's good. Which of the following actions would change the measured cell potential? And we do have the option of any of them would change. This is where Le Chatelier principle comes in. Remember that these are standard of 1.0 molar. Both of these are 1.0 molar. Actually not this one, because that's not the aqueous solution. This one over here is 1.0 molar. Okay, so if you add something here, it's going to drive it this way according to Le Chatelier. If you add it here, it's going to drive it that way, or take it away, it's going to drive it that way. So increasing the pH at the cathode compartment. The cathode is where reduction is taking place, and it appears like the hydrogen here is what's reduced. So if you increase the pH, add more of this, that will work in your favor. So yeah, that's a good one. Lowering the pH in the cathode compartment. So in the cathode compartment, lowering the pH, increasing the pH. Increasing the pH in the cathode compartment. Now wait a minute, no. I'm going to go back. This is adding hydroxide to it. It would seem to me that increasing the pH would be like to take this away, and that should actually decrease the potential. So my guess is actually this one here would change. Well, it's just a matter of changing it. Well, any of these would change it. So no, I'm gonna back off on that one, because it's just asking for something that has a change. Well, what am I thinking? That will cause a change, and guess what? That will cause a change. Increasing that will cause a change, because if you increase this, it's going to change it that way. Increasing the pressure of hydrogen gas in the cathode compartment. Well, yes. If you increase the hydrogen gas potential, that's the same thing as adding some of this, and that would force it this way. So yeah, any of these would be likely to change the cell potential one way or the other. Okay, gaining electrons is called reduction. What's the oxidation number of chromium in this? Okay, so again, I'm going to show you how to figure this out. You have to make a box. Let's divide up these elements. And okay, so the whole thing is 2 minus, you see that? This whole thing is minus 14. And this side is going to be plus 12, because you see it's going to net out to minus 2. So this whole side has to be plus 12, because now, see, this plus this is equal to that. However, we do have 2 of these chromiums, so this is going to have to be plus 6 and plus 6. So the answer is it's plus 6. See how easy that is? Now the oxidation number of potassium here. Potassium is really the cation in this, and of course, as you know, potassium is plus 1. The permanganate here in this one has got to be minus 1, and you'll see if you look it up in the book that it is. So in fact, the charge on the potassium is plus 1. It always is. It's never, the alkali metals are always plus 1. What is the oxidation number of the manganese in this? So minus 8 is equal to minus 1. This has got to be plus 7. Yeah, that's pretty easy. Okay, so plus 7. What's the oxidation number of oxygen in this? Here is one of the rare cases where oxygen you see is, I'm going to just write it out like this so you can see. The hydrogen here is +1, +1, and so this whole side here has to be 2 minus. But then notice that means that each of these oxygens has to be +1. Most of the time oxygen is 2 minus, but in this case it's actually 1 minus. This is the peroxide ion. Okay, electrons appear in the following half reaction when it's balanced. How many electrons will appear? So what I would do is, let's just figure this out. So S4O6, 2 minus. Here we have 2 S2O3s, 2 minus. Well, let's go ahead and try to balance this. So I have 4 S's here, 4 there, that's good. I have 6 oxygens, and I have 6 oxygens, so that's making it easy on us. Here I have -2 on this side, and over here I have -4. This is 2 times -2, so see, there's the problem. -2 to -4. I have to add electrons to the less minus side to make it equal to the more minus. So really, this is going to have to be 2 electrons added to this side of this half reaction will balance it out. So the answer here has to be 2. The electrode at which oxidation occurs is called, you see, O goes with R. So this is it's called oxidation occurs at the reduction, so it's going to be the cathode, because R and C are both consonants. Hang on a second, let me back off from that. I need to re-explain this. So okay, so I wasn't thinking clearly. Oxidation is when you lose electrons. So oxidation happens at the anode because of O and A. Okay, there I said it correctly. So oxidation occurs at the anode. Okay, the half reaction occurring at the anode of the balance understood as below is occurring at the anode. So like I just said, oxidation occurs at the anode. Alright, so which one of these is the oxidation side? So what's being oxidized here? Maybe is it the iron? Iron's going from 0 to +3. That sure is oxidation. And so from 0 to +3, is that one of our options? 0 to +3. I would say that's where the oxidation is taking place. The reduction is probably this. I think this manganese is +7 here, and over here it's gone down to +2, so that's reduction, which would be the cathode. Standard cell potential for the voltaic cell up below is, okay, let's figure this out. We're going to take the one that's reduced minus the one that's oxidized, so it's gone from +2 to +4, that's oxidized. So the 10, and then on this one is gone down. So the 10, 4 to 2, it's going to have to be the second one here because it's oxidized. Subtract that off like that from the other one, which is 3 to 2, 3 to 2, 0.771. Okay, so 0.771 minus this. So really it's going to be minus 0.154. Okay, so what is my answer? So the answer is it's going to be a positive 0.617. Now this is just a formula. The correct formula relating electrochemical cell potential to spontaneity, or delta G, is this one. That's just definition. Okay, so what's the cell potential here? Looking up this data and the appendix of the book, you find out that the lead half reaction going from 2 plus to lead metal is a negative 0.126. The other half reaction, which is silver ion going to silver, so this is the reduction side, that is a positive number, 0.799. Okay, so then what we can do is we realize this is reduced and this is, okay, now the number that's more negative is going to be the one oxidized. That's just what you do. So this is going to be the reduced side minus the number that's more negative. So see, that's when you add, we're going to need to add them together, and looks like it's going to be positive 0.9. It's got to be this one. Okay, and here's the last problem in this entire set. So let's take a look at this. You need to label things. And so I noticed that the zinc here is being oxidized. It's losing electrons. Copper is being reduced. So the compartment where oxidation occurs, label with point A. Oxidation is going to take place on this side. Compartment where reduction takes place is going to be this side. Salt bridge is this thing right here. Direction of electron flow. So notice the electrons are leaving this side. The electrons are leaving this side and they're coming down here. So you needed to draw an arrow showing the electron flow in that wire. The direction of the ion flow in the salt bridge. So the positive and negative ions. Since positive is building up on this side, because you see the zinc is actually turning into this ion and it's filling up the solution. That means that you have to bring in negative charges, you see, so you want to show that the negative charge is going that way. And then of course over here, negative charge is building up because these ions are getting reduced onto the electrode here. So in this case we have to replace the positive ions that are getting lost with these positive ions. So negatives go that way and positives go that way. So the anode, again, that's where A is where oxidation takes place and C is where reduction takes place. So the anode is right here, labeled D, and the cathode is where reduction takes place, and it should be over here, E. Okay, so that's pretty much it. Now we have to finally calculate the E cell potential for this. Okay, now I need to look up zinc, and when I do that, I find out, see, the zinc is going to be the one that I reduced, but the zinc is a negative 763 when you look it up in the back of the book. The copper is a positive 0.337. Okay, so very simply, you just have to take 0.337 minus a negative 0.763, and you get a total of 1.1 volt difference. So it's 1.1 volt. You really should show me this work and not just write down some answer that I won't know if you know how to think it through if you don't just write down your answer. Okay, so that's the end of the podcast. Just a little bit shy of 30 minutes. Hopefully this was helpful and you learned something. Thank you.